Okay. Yeah. So last time we talked about tensor product of modules, but when you specialize to vector spaces, you can think of them as more concretely as a so tensor product of two vector space V and W as a vector space whose dimension is same as dimension of V times dimension of W. Together with this bilinear map from V cross W to V tensor W, which sends V comma W to the element V tensor W. And V tensor W is the vector space whose elements you can think of it as sums of these kind of terms. Yeah, or you can more concretely you can think of them as the vector space generated by symbols Vi tensor Wj, where V1 to Vn forms a basis of V and W1 to Wm forms a basis of W. Yeah. So of course, if you change the basis, then then also you get. I mean, nothing changes. Yeah. So you'll get a new set of bases for V tensor W, but the elements don't change. Yeah. So does this make sense? So what I'm trying to say is tensor product in vector spaces is fairly concrete. Yeah, no, you don't have to go through that abstract definition as such. But if you want to define it in more generality over rings, then this method doesn't work somehow. Yeah, because you know, there are modules which are not free and so on. Yeah. So torsion modules and so on will create problems. But for vector spaces, it's fairly explicit what tensor product of two vector spaces. Any questions so far? Okay, so we will define, what we'll do is define tensor algebra over V. Yeah, today we'll also see symmetric algebra, exterior algebra. So tensor product we have defined, we'll define symmetric product and exterior products and so on. Yeah. So what is so what are tensor products? So if you are given a vector space V, we define T2 of V to be V tensor V. Yeah. So if V is n-dimensional, what is the dimension of this guy?
N square, right?
N square.
Yeah, so this is same as dimension of V whole square. Yeah. And so T2 T square V is straightforward. Similarly, you have TQV. Yeah. So TQV is basically you take T2V and tensor it with V. Yeah, or it's V tensor V tensor V, and it doesn't matter which order you tensor it. So first you do the first two guys, and then tensor the third, or you do this. They are all isomorphic. And so one denotes it by triple tensors. Yeah. So so elements of this you can think of it as so this triple tensor product you can think of it as a vector space whose basis is EI tensor EJ tensor EK, where IJK varies between 1 to n, and if E1 to En is a basis of. Yeah. So it's fairly explicit what this vector space is. Right. And it again comes with a multilinear map now. Yeah, instead of bilinear, it's a multilinear map. Yeah, so there is a multilinear K multilinear map, trilinear if you like, but you won't go very far with this map. V cross V to T3V. Yeah, which sends V1, V2, V3 to V1 tensor, V2 tensor, V3. Yeah. So of course, every element in T3V doesn't look like the image of this trilinear map. Yeah, it's sums of this. And this is fairly easy to understand, right? Because what is the dimension of the left-hand side? V times V times V.
N cube.
No, left side. V
Okay.
V cross V.
Thrice.
Thrice,
V
right?
times N, yeah. I mean, V has dimension N and W has dimension N, then V cross N, W has dimension N plus M, right? With the basis being you take the basis of V and then adjoin the basis of W to that list. So this the left hand side has basis has dimension 3n, while the right hand side, as someone said, is n cube. Yeah. So n times n times n. Yeah. So we this guy has dimension n square. This has dimension n. So the whole thing has dimension n cube. Right. So you can see that the image of phi is going to be some. So it can't be. So first of all, phi is also not a linear map. Yeah, it's a multilinear map. Yeah, so it's not a morphism of vector spaces. Okay, so if you take so you can check that the sum of two vectors doesn't go to the sum of in their tensors. Yeah, it goes to something else. So this is K multilinear. So this is not even a vector space map. It's a multilinear map. And secondly, even if so, the dimensions are also off. Yeah. So so for instance, the sizes in some sense are different. If K was a finite field, then of course this will this is left hand side is a much smaller set than the right hand side. Yeah. If the field is infinite, then all the cardinality matches. But in I mean, but as vector spaces, the dimension don't match. Yeah. So there a reasonable map doesn't have any chance of being a bijection. So though phi is not a vector space map, it's still a somewhat reasonable map. It's a multilinear map. Okay. So so more generally, if you have T and V, you can define it as tensor product of n copies of V. Yeah. If n is greater or equal to. If n is so by convention, if n is 1, then T1V is just V. And if n is 0, then the convention is T0V is the base field K. Okay. So the first two lines are convention. So this is by convention. Okay. So this is and these are various tensor powers. So for each n, you have some tensor powers. 0 tensor power is the base field. 1 tensor power is the vector space itself. 2 tensor powers, and so on. Also, not only you have multilinear map from V cross V, and again to T and V, you will get a multilinear map. Yeah, from V cross V up to n copies to tensor product of V with itself n times. Yeah, that will be a multilinear map defined in the same way. Okay, but there is also a bilinear K bilinear map from Tn cross V to Tm cross V. Yeah. And what does that K bilinear map does? So Tn cross V, say you take an element alpha of Tn cross V and take an element beta of Tm cross V, then you send it to alpha tensor beta. Yeah. So all this makes sense. So 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 one has to check that all this makes sense, yeah. So if you are doing tensor product, so as I said, giving a map from tensor product. Yeah, so maybe I should have written a little more here. Yeah, so maybe I'll write it here. So as I said, giving a map from tensor product is not an easy task, yeah, because it's not in general it's not a free R module. It's some abstract module, but here. Of course, it happens to be, since you are in the vector space setup, it happens to be nice vector space. But you can make this fairly explicit, yeah. So you know that okay, so maybe you know that there is a multilinear map from V cross V to T and V, yeah. I don't know, maybe let's label it as phi n, yeah. K multilinear. So slowly I'll drop this letter K, yeah, which sends you know, the n tuple V1 to Vn to their tensors. So so to give a map from and TMV is similarly a map from V cross V to some m copies of V to m tensors of V. Yeah. So to give a map from K bilinear map from TNV cross TMV to Tn plus MV. So yeah, so instead of doing abstractly, what I'll do is write it explicitly what this means. Yeah. So what does an element, how does an element alpha in TNV looks like? So alpha is so suppose E. So we will take let. Yeah. So now. Yeah, so let's declare the dimension of V to be, let V be R dimensional, so that I have to make minimal changes, and vector space, and V E1 to ER is a basis. Yeah. Then alpha, you can write it as a summation E. Yeah. So what's the best way to write it? Yeah. So as you have to use multi-index. So okay, I'll put the index later. Let me just put the vector first. E. So it's a multi-sum and multi-index. Yeah. So EI1 tensor EI2. How many times the tensor will be there? So we are trying to, so alpha is an element of T and V, yeah. So alpha, you can write it as EIN, EI1 to EIN, and A, so one should put this in this I twiddle, yeah. So and I twiddle is basically this index I1 to IN, yeah. So this belong, so you where I1 to IN are numbers, yeah. I1, so maybe I sub j is between 1 and R for j for all j 1 to n. Yeah. So we know that the basis looks like these guys, right? Ei, Ej, Ek. For 3 terms, it's Ei, Ej, Ek, and I, J, K are between 1 and n. Yeah. So if you have for T cube T cube B, for Tnv, it will look like by this analogy, Ei1 tensor Ei2 up to Ein. Yeah. And there will be this collection will be a basis. So every alpha you can write it like this. Yeah. And similarly, beta you can write it as summation b. Okay, I've used up all my indices. Yeah. B. K, L, maybe L, B, L, twiddle, E, L1 to E, L, M, yeah, because it's in T and M, yeah. So L tilde is, and this tuple, L1 to LM, and the sum, so L1 to LM can vary between 1 and R, yeah. Lj is between 1 and R, J between 1 and R. Okay. So this is how this beta will look like, and so their tensors make sense, yeah. You can so if you do the tensor product of these 2 terms, you just do it term wise, yeah. Ei1, Ei2 up to Ein, you tensor it with El1, and then further tensor it with El1 to Elm. Then what you get is an element of T. You'll get a basis vector of Tn plus Mv, yeah. Right? Is this making sense, everyone?
Yes, sir.
Yeah. Okay, good. So you see that this when I don't see faces, it's not very clear if everything is making sense. Yeah. So this is so since I have defined it explicitly what the map is. So if alpha is this, you know what alpha and beta is this. So alpha and beta looks like this. The tensor product will you can write down an explicit formula. So then it is well defined. Yeah. What alpha tensor beta is. You just take the tensor of this and you do the usual tensor manipulation. Yeah. So it's going to be AI BL L AI vector summation over these 2 terms. So you expand it, use the distributive law. Yeah. And you get alpha tensor beta. So the formula will look a bit complicated, meaning it will become a little long, not complicated, just long, but it will give you what alpha tensor beta is. Yeah. So and then one has to check that it is bilinear. Yeah. So it's linear in. So TNV is a K vector space. TMV is a K vector space, and this map is bilinear. Okay. K bilinear. So so this is called tensor products. Yeah. So you can tensor product of tensor powers. Yeah. So if you are given 2 tensor powers, one is nth power and one is nth power, you can multiply them and get n plus m powers. Yeah. Or this will be the product in the tensor algebra, which we are about to define. Yeah. So what is a tensor algebra? So there are multiple ways of defining it. So I'll give you one definition, which is constructive. So T dot V, you consider the as a abelian. So to give a K algebra, you have to give a K vector space together with multiplication. Yeah, in that vector space. How do you multiply? And that will give it a algebra structure too. right? So the K vector spaces, you just take the sum of all these T and V's which we have defined. Yeah. So more explicitly, maybe I can write it here. It's K plus V direct sum V plus V tensor V plus tensor V so on. Okay. So each T, if V is finite dimensional, each T and V is finite dimensional, but of course the tensor algebra is not. Yeah, it has infinitely many terms. So that's an infinite dimensional K vector space, but it's an algebra. So and it has some sort of universal property which we'll see. So you expect it to be a big space. Yeah. Big vector space. So then this guy T dot B is a K algebra with multiplication defined by this. Yeah. So I have told you how to multiply an element in TNV and an element in TMV to get an element in TN plus MV. Yeah. So if you are given an element in TNV and one element in TMV, you can multiply and get something in TN plus MV, which is also a subset of T dot V. Yeah, the tensor algebra. Now, but of course, not every element of tensor algebra is an element. You can't say it's an element of TNV. Yeah. What you can say is it's you can decompose it in as sums of so yeah. Okay, so I'll come to this proposition maybe, or let's see if I can edit this. Not very well. Let me try again. Okay, yeah, so this is reasonably well. I will erase it. Yeah. Okay, so so if I take an element alpha in T dot V, then alpha we can write it as so you can uniquely write it as first term in K T0V. So you can write it as, maybe I'll write it this way: alpha 0, alpha 1, and so on, alpha 2. So so all but finitely many will be 0 because it's a direct sum, but where alpha I belongs to the TIV. Yeah, by definition of this direct sum. Yeah, by definition of the tensor algebra. And then of course we know how to multiply. So we know how to multiply an element in TNV and an element in TMV. So we will just use the distributive law. Yeah, that beta n belong to T dot V, and beta also we can write it as summation beta I. And this is unique, yeah, because of the direct sum. There is no choices. So there is a unique element alpha 0 in K, alpha 1 in V, alpha 2 in V tensor V, such that alpha is direct sum of these guys. Beta I and TIV uniquely. Both places, yeah. So alpha, so I'm trying to define multiplication of alpha with beta dot beta in T dot V. Alpha dot beta is defined to be summation. Yeah, so yeah, so I'll tell you as an element of TV. So Let me write it concretely first. So alpha 0 plus beta 0 is the element of K, plus alpha 0 beta 1 plus alpha 1 beta 0. That's also that's vector space. So I mean, this beta 0 you can put it here, but maybe I'll put it as tensors. Yeah. So with the convention that K tensor V tensor K and K tensor V is V itself. Yeah. So here you can move it in front as well. But for the next few terms, it's sort of difficult. You can't interchange the order. So tensor algebra is not abelian. It's not a commutative ring. Yeah. So this is alpha 0. Yeah, so alpha 0, so the beta 0 and alpha 0 are in field, so that you can always change places, but yeah. So maybe, yeah, so maybe here I won't put tensor. Yeah, this is just scalar multiplication. But we will, with the convention that in which order we multiply is not very, on which side we multiply is not very, it doesn't matter. But alpha 0, alpha 2, sorry, alpha 0 beta 2 plus alpha 1 tensor beta 1. So these are really tensors. Beta 2 is already in T2V. So this term is in. So this term is in T1V, which is same as V. This beta 2 is already in T2V. If you multiply it by an element of the field, it remains in T2V. Alpha 1 is in T1V, beta 1 is in T1V. And if you do this multiplication, which we defined here, yeah, you get alpha 1 tensor beta 1, which is in T2V, and so on. Yeah, plus, what do we get here? Alpha 2 times beta 0. Yeah, so beta 0 is an element of the field. You multiply it with an element of T2V, you still get something in T2V. So this is in T2V, and so on. Yeah. So the next term is sort of complicated to write. So we'll use a formula. Yeah. So this is alpha dot beta is summation. So maybe, so it's like when you multiply two power series, you have this kind of formula. Yeah. So I equals, or maybe yeah, I equals 0 to infinity, and here j equals 0 to I. Alpha j tensor no, this is not sum, this will be product. Yeah, no, this is sum. What am I writing? Summation j equals 0 to I. There are two terms. Yeah, so it's okay. Alpha j tensor beta I minus j. So that will lie in beta I. Yeah, in TIV. So you take these sums. So the for I equals 0, you get an element in the base field. Yeah, because there will be only there should be only one. There will be only one term. I equals 1. There will be two terms, and so on. Yeah. So this looks okay. Yeah, I think this is okay. Yeah, so this is the formula for alpha dot beta. If alpha is this particular element of TIV and beta is this particular element of TIV, then alpha dot beta is this particular, and this of course belongs to T dot B. So you just so of course one has to check that this is a ring. So meaning so it's a group under addition, that is clear. So you have to check whether whether a multiplication is associative or not. So associativity one has to check, and one also has to check distributive. Yeah. So all that you just have to check at this level. Distributive is more or less forced. Yeah. So it's we are trying to force the distributive law. Yeah. So, but anyway, one has to check that this is an algebra. This is indeed a ring. Yeah. And hence becomes a K algebra. Okay. Is the
graded algebra over K, right?
Yeah, it's also a graded algebra, but in particular a K algebra. Yeah. So graded is something which I don't know if you have seen, but if you know it, what a graded algebra is, also a graded algebra. But if you don't know what graded algebra is, you don't have to worry about it. Graded algebra means you can decompose it like this. There is a grade 0 piece, which in this case is K. There is a grade 1 piece and so on. Yeah.
It's this TKV, right? The grade K piece.
Say that again.
The grade K piece will just be TKV, right?
Yeah, the graded pieces are the graded pieces are TNVs. Yeah, T or TKVs. So these are the graded pieces, and this is what a graded ring means. It precisely means that if you multiply the nth graded piece with the mth graded piece, the element should land in n plus mth graded piece. So this is what a definition, more or less the definition of graded ring is. Yeah. But if you don't know, don't have to worry about it. Yeah. So this is the constructive way of saying what a tensor algebra is. You could another way to define tensor algebra is somewhat abstractly, like we defined tensor product of modules. Yeah. So you define it using a universal property. So in fact, instead of but we have already shown that this is a tensor algebra. What I'll do is the universal property I'll use I'll prove it as a proposition. Yeah. So let V be a K vector space, A be a finitely be a algebra. Yeah. Be a K algebra. Okay, this is the correction. Phi from V to what is this? A. Yeah. V to A be a K linear map. Then there exists a K algebra homomorphism phi tilde from there exists a unique. Yeah, unique is important. K algebra homomorphism phi tilde from T dot V, the tensor algebra over V, to A, such that when you restrict this phi tilde to T1V, and what is T1V? Remember, T1V is same as V. Yeah. So it gives you a map. Maybe I'll not write it here. So it gives so phi tilde restricted to T1V is a map from V to A. Yeah. So this should agree with the given map phi from V to A, the given K linear map. Okay, so then so this is what so this is like a universal property. Any K algebra and any K linear map from V to A, you can get a algebra map from T dot V to A. Yeah. So another alternative way of defining the tensor algebra would have been tensor algebra is over of V is a K algebra. I could have said it's a K algebra T dot V, let's say, together with a K linear map, from V to T dot V, such that given a K algebra A and a linear map V to A, there exists a unique map from T dot V to A, such that this diagram Yeah, like we defined in tensor product. And then one could show that this is unique up to unique isomorphism, and then one can prove the existence. And of course, proving the existence is precisely this game. Yeah, you construct this tensor algebra this way, and so that this has the universal property. Yeah, so once we prove this universal property, then you can use this proposition to define it alternatively as well. Okay, so let's see why this universal property is true. Yeah. So proof. So maybe I'll do this in the next page. So I've been following this technique of making this small and then writing it here, with the hope that this is helpful. So are you guys able to see what is on the left side, or is this too small to be useful?
It's still visible. It's readable.
It's readable, yeah. It's not completely useless. Okay, so so we'll prove this proposition. Okay. So yeah, so unfortunately this went down, and I don't want to make it. Is it still readable? Okay.
Yeah.
Okay. Okay. So let's write down a proof of this proposition. So maybe yeah. So the first part we can remove. So I can write from here. Okay. So we want to prove that there exists a unique phi tilde such that T dot V to A and a K algebra map T dot V to A such that this happens. Yeah. So let's try to construct this. So there's only one way to write down this morphism. So we'll write that way. Yeah. So yeah. So let's get to the definition of phi tilde, and then we will show you it's unique. Yeah. So phi tilde. Hopefully this is okay. T dot V to A. We want to define phi tilde from T dot V to A. Yeah. So we so we already know what is the map from T1 to T1 V to A. Yeah. And A is a K algebra means what? So there is some structure map. Yeah. So which the data is not given. Yeah. So let's try to write that information. So K algebra means there is a map alpha from K to A. Yeah. Which makes A into a K module. Yeah. So so A is a K algebra means this, where this one will go to one of A. Yeah, this is what. So let's not call it alpha because too many things are being called alpha. So I don't know what to call it. So maybe S for structure map. Yeah. So S is this. Be the map which makes A K algebra. Yeah. So that is what K algebra means. Yeah. It's a ring together with a map from K to A. Yeah. So which sends 1 to 1A, and this map should be a ring homomorphism. Okay, so how do we define this? So yeah. So how do we go about doing this? Yeah. So Yeah, so phi, so let's define it in each graded pieces. So phi 0, we define it from T0V, which by the way is same as K, to A to B S. Yeah. So phi 0 is same as S. Okay. Phi 1 from T1V to A. T1V is same as V. Is the given map is phi. Okay. And then phi 2 we will do, and then in general we'll define phi and b. Yeah. So phi 2v is a map from so T2v to A, and then we will add them and show that it's a ring homomorphism. Yeah. So phi 2 from T2v to A, we want to define. So this is V tensor V, and A is a ring homomorphism. So so you define it to be yeah. So so of course yeah. So yeah. So how do I define it? So V cross V to A, we have a map which is induced by phi 1. So V1 comma V2, you send it to phi V1, sorry, S, yeah, phi V1, which is an element of A times phi V2. Yeah. So, and you can check that this is a bilinear map. Yeah. So if you, because phi is a K vector space, is a map of K vector space. So if you fix V1, yeah, so and you vary V2, then it's linear in V2. Yeah, because phi is K linear. Yeah. So this map, let's call it C, from V cross V to A is to A is bilinear, and hence it induces a map to the tensor products. So this so C so it induces by universal property of tensor product, it induces C C tilde V tensor V to A, which sends V1 tensor V2 to phi V1 V2. Oh, sorry, so space is a bit of a constraint, so maybe I'll write it here. Which sends V1 tensor V2 to phi V1 times phi V2. Okay. So phi 2 is C tilde. So phi 2 is C tilde. Okay. So so this map, so I've used the universal property of tensor product, but one can, so you know what this map is explicitly, because the tensor product of V with itself is somewhat explicit. So what you have to do is it is every term here is not of the form V1 tensor V2, but sums of this. So you just so for each, but it's generated by these kind of elements. So for each element, you know where it's going to go, and then you extend it linearly. Yeah. So phi 2 of alpha, alpha 2, where yeah, so maybe this way. So if alpha 2 is in, so I'm trying to do it in more detail than maybe is necessary, but V tensor V, then alpha 2 is of the form summation Vi V alpha VB V alpha V too many alphas. So two sums of two kinds of vectors, two vectors, yeah. Sums of tensor product of yeah. So maybe V tensor V prime, but some indexing I should put. So maybe I. This is finite. So there are only finitely many terms in this sum. Yeah, so our typical element here in T2V looks like this. Then phi2 of alpha, which is same as C tilde of phi2 of alpha 2, which is same as C tilde of alpha 2, looks like sum of phi of Vi times phi of Vi prime. Okay. So this is how phi2 is defined. Yeah. So so it's enough to define on a basis. Yeah. So these are all vector spaces. So it's enough to say where a particular basis vector, where the basis vectors go, and then it is extended linearly. Yeah. So for the higher ones, I'll just tell you where the basis vector goes. Yeah. So phi n from Tn V to A. So we know what the basis vector is. So let V, let EI E1 to ER be a basis of V. Then then we know what a typical basis vector here looks like. You just have to take tensors of EIs to ER, n tensor power of EI to ER. Yeah. Then phi n of I1 tensor EIN, where is equal to phi of, so EI1 is a element, is one of these EIRs, yeah. So it's what you just send it to phi I1 times phi EI2 times phi EI. Yeah. So once I tell you what happens to the basis vector, you know what the map is. You just extend it linearly. Yeah. So phi n's are maps, K-linear maps of vector spaces from T and V to E. Okay. So far so good. Yeah, everyone.
Yes, sir.
Yes, sir.
Yeah.
Yes.
Yeah. So now you can define phi from T dot V to A to be phi of alpha is phi of alpha 0, phi 0 of alpha 0 plus phi 1 of alpha 1 and so on, where alpha in T dot B is uniquely, you can write it as alpha 0 plus alpha 1 to so on, where alpha I belongs to TIV. Okay, so this is the definition of phi. Then finally, one has to check that this is a K algebra homomorphism. Yeah. So to check, this is a key algebra, and one has to check. So by definition, we know that phi tilde restricted to T1V is phi, and that was the definition. Yeah. So one only has to check that this is a key algebra homomorphism, and then finally one has to check that that it is unique. So uniqueness is not going to be difficult because it's somewhat minimal. I mean, there were no choices in some sense. So let's first check that it's a key algebra homomorphism. Yeah. So of course, these are all these behave well with addition. Yeah. So to check some because so note maybe right. So note that phi's are k-linear, hence phi behaves well with addition. So addition is not an issue, meaning if you take two elements alpha and beta, then phi of alpha plus beta, alpha and beta in T dot B, then phi of alpha plus beta is going to go to phi of alpha plus phi of beta. We'll check for multiplication. Yeah. So let alpha beta be in T dot B. Yeah. And then phi of alpha dot beta, we have to show is same as phi of alpha times phi of beta. Yeah, so this looks complicated, but we had this formula. Yeah, alpha dot beta looks like this guy. Yeah, so we'll use that formula. So this is summation sum of I equals 0 to infinity summation alpha j beta I minus j j equals 0 to I. Yeah, so this is how sorry, phi of this guy. So it's phi of this whole guy. Yeah, and by definition, phi of this is phi I of whatever is in this smaller bracket. Yeah, so j, so sum I equals 0 to n, phi I of j equals 0 to I, alpha j tensor beta I minus j, which and we know what the definition of this is. So this is I equals 0 to n. Phi I of so phi I is linear, k-linear, so we can take phi I inside, and phi I of alpha j times beta tensor beta I minus j is just you take the images and multiply. That is what this definition was. Yeah, right here. So this is same as j equals 0 to I phi I alpha j sorry, not phi I, but now it should be yeah. Yeah, so actually it should be phi j. Yeah. So alpha j is in a tj. Yeah, so one has to, yeah, so yeah. So yeah, so it's not very convenient to write. So is yeah, if it were two terms, it would be yeah. So this is so maybe check this, yeah. So but it works out. So so this is so phi j of alpha. So okay, maybe not. So let's do it in two steps, yeah. So I'll tell you. So this will be easier to explain if I do it in two steps. Alpha j times beta I minus j. Yeah. Now phi I of alpha j times beta I minus j. The way things are defined, so alpha j is in the first is in TJV, yeah, and so you can write it as in terms of basis vector, you can write it as some linear combination of these kind of guys, and beta ij similar I minus j, you can write it similarly in terms of other guys, other basis vector, and you can verify. So this is what I'll do. I'll ask you to check yourself, yeah. Using maybe basis vector, that this is same as phi j of alpha j times phi I minus j of beta I minus j. Yeah. So remember what does phi j does? It looks at various components and decides where. So you know it bases it as. Yeah, so anyway, to show the equality, I'll have to break it down to that level. Yeah. Yeah, so I'll have to break alpha j's. So yeah, so then yeah. But I hope this is clear to you. So alpha j is summation, some linear combination of ei1 to eij. Yeah, linear combination of ei1 tensor ei2 tensor eij. Yeah, and beta I minus j is similarly some linear combination of some similar tensor. Yeah, and then on each factor is just phi. You apply phi. Yeah, so this is going to be same as yeah. Yeah, so or maybe this is enough, yeah. So this maybe now you can write it as I equals 0 to n. Yeah, so I think this is enough, yeah. So you don't have to break it further. So you just sum it alpha j times summation j equals 0 to n. So just changing. So it's not maybe. Yeah. So you can write it as sums. So maybe I'll write it differently. Yeah. So you can write it as. So this is how we got this formula as well. Yeah. We multiplied sums of alpha and sums of beta to get this thing. Yeah. So similarly, you can write it as yeah. So this is not bad. Yeah. So this you can write it as P0 alpha 0 plus P1 alpha 1 and so on times Phi0 beta 0 plus Phi1, because this is happening in the ring A. Yeah. So all the distributive properties, etc. work. Beta 1 plus, yeah. So if you multiply these terms in A, so most of them are, so this is a finite sum. So maybe I should put the last term here. Actually, yeah, so it's difficult to put the last sum because I don't know where this alpha ends. Yeah, so but this is a finite sum because as we agreed, all but finitely many alpha i's are 0. Yeah, and similarly, all but finitely many beta is a 0. So both these terms are finite, and you are multiplying these two together to get this. So I don't know why I put n suddenly here. This should be infinity. Yeah. So though the sums are till infinity, but most of them, but they are all finite sums. Yeah. So by distributive law, you get this, and this is precisely phi of alpha times phi of beta. Okay. So if you multiply this two, you get the first term is phi 0 of alpha 0 times phi 0 of beta 0, which corresponds to the term I equals 0, and so on. Yeah. So phi is a ring homomorphism. Okay, so sorry, I think maybe these checks take a bit of time. Maybe uniqueness will be a check uniqueness. Uniqueness of phi tilde. Phi tilde, sorry, this was phi tilde. Phi tilde. Okay. So phi tilde, phi was the given map, and of course check uniqueness. So that will complete the proof. So it's already time, so I'll have to stop. Okay. So you just verify uniqueness, and that will complete the proof of this thing. Any questions? So maybe I'll stop recording.